In this example, we've collected some velocity data off of our jet, and we're trying to determine what the acceleration of the jet is over the same time period. This is in contrast to a very similar example we looked at last time, where we were looking at integration. We were given the velocity data, and we could integrate it to get the position of the jet. So the derivative of velocity will give us the acceleration, where the integral of velocity gave us the position. So I want to start by entering my raw data. So my independent variable time just goes from 0 to 11. One difference we see in this example, time is uniformly sampled 1 second apart. In the integration example, it was not uniformly sampled. Right, so I have my time and I have my velocity, which I'll enter in here. So 3.1. Six. And I just want to have an idea of what this looks like. So I'll plot it. And 1, 2. Yep, it looks like I missed one. 64.9 was missed. All right, now they're the same length. And with our labels here, this is our time in seconds. And for this, my dependent variable is my velocity. And this is in meters per second. Alright, so that's what my raw data looks like. Let me also put in those data points. Like with integration, I'm only going to be able to get these estimates at the same locations that my time samples were. So I'm only going to be estimating the acceleration at 0, 1, 2, 3, 4, 5 seconds, etc. Like with integration, if I want to know what's happening between, I could use interpolation or some other method to make that assessment. So the premise is I want to know the acceleration at all of these data points, so I want to make an estimate as to what is the slope at each of these points in time, 0, 1, 2, 3. And I'm told in the problem statement I want to use an accuracy 2 method, and I want to compare using forward differentiation, backward differentiation, and central, and seeing all the differences that they have. So I'm going to start by looking at the forward differentiation. I'll call my derivative dy, and I will pre-allocate it here, and it's going to be the same length as v. I guess I'll call it a since it's acceleration. All right, so I know I'll have 12 values at each of the 12 times that I've sampled. So with forward differentiation, with an accuracy 2, if we go back to that table that we saw earlier on slide 8, at accuracy 2, I have to use the kth value, the k plus first value, and the k plus second value to calculate my value of acceleration, or my value of the derivative. So I can do this in a loop. So I'll go from k equals 1 to length of a. So for the first value, when time is 0, if I want to know the acceleration there, well, I have to know the value of my function at the kth value. So that will be v of k. And if I look at the table for accuracy 2, I'm going to multiply that by -3 over 2. Then if I look at the table, I have to use the k plus first term of my dependent variable. So that's v of k plus 1. I'm going to multiply that by a +2. And then for second order accuracy, if I look at the table, I'm going to use the v of the k plus 2 term, and that gets multiplied by a -1 over 2. And then that whole thing gets divided by the step size, which in this case is 1. And I will explicitly put that at the beginning that my dt is going to be 1. And we're going to see in a second here what the problem is if I just use forward differentiation, try to use only forward differentiation. So again, as the value of k increases, then the value of v I'm referencing changes. When k is 1, I'm finding the value at time is 0, since that's the first value of time. So I use the first velocity, the second, and the third. Then k increases by 1, so I'm looking at the second time. So when time is 1 second, so I use the second value of velocity, the third, and the fourth. But if I try to run this, what happens here is I can't, because by the time I reach the second to last value, I can no longer use the forward differentiation, because I'm trying to use the 11th value as my v of k, the 12th value, that's okay, and the 13th value, but that's not okay, because I don't have data for the 13th value. So in this case, I can't use forward differentiation for the whole thing. I'll use it for the most part, but I can only use it until k is equal to 11. Or when it's less than 11, I can use the 10th because I can use the 11th and the 12th, but I can't use the 11th and I can't use it for the 12th. So what I'm going to do, and some of this I can recycle into the second part of this, is when k is greater than 10, or when it's 11 or 12, I'm going to use backwards differentiation, because I will have enough data to do that. So if I look at the table, it's going to be pretty similar here. First of all, remember for the first derivative, the coefficients are going to be negated. So that goes to a positive 3 over 2, a negative 2, and a positive 1/2, because I negate each of those. And also, instead of adding values to k, I'm taking the k minus 1 and the k minus 2 value. So again, here I'm actually using backward differentiation, but for most of it, I am using forward differentiation. So again, what happens here, we don't run into that problem because it doesn't try to use forward differentiation once I get to the 11th value. It then will switch to using backward differentiation with the same accuracy. So again, look at the difference between the two when I'm using the forward and the backward differentiation. Forward, I'm using the signs on the value as indicated on the table, and I'm using k, k plus 1, k plus 2, etc. For the backward differentiation, I have to negate the signs given to me on that table, and I use the k minus 1, and the k minus 2 value. So now what I can do is plot the estimate as to what the derivative is. And let me make it look nice. And this is now my acceleration. And that's in meters per second squared. So using forward differentiation, this is what my estimate of the acceleration of the jet looks like over time. So it starts with a high acceleration or a high slope, and then eventually that slope goes to 0. It has its maximum value around 7 seconds, and then it actually starts to decelerate after that. Let me go back to the original plot. I'll actually do this as a subplot. That way I can see what they look like at the same time. Right, so the lower plot, the acceleration, is trying to estimate the slope of the velocity plot. So you see here where we have that 0 crossing, we have that maximum velocity. The velocity starts to go down, therefore the slope becomes negative. Therefore the value of the acceleration we should also expect to be negative there. And I'll give this the title. We did this with mostly forward differentiation. Alright, now I want to compare this to using mostly backwards differentiation. A lot of this I can recycle. I don't have to reinvent the wheel here. So I'll reallocate A back to zeros. Now I want to use backward everywhere I can, and forward anywhere I can't use backward. So keep in mind, to use backward differentiation, I need the kth value, the k minus first, and the k minus second. So the problem I'm going to run into here is that if I try to use backward differentiation when k is 1 or 2, it's not going to work because I can't take k minus 2. I can't reference the 0th value of v or the negative first value of v. So what I want to use here is I want to use backward only when the k value is greater than 3. And I'll actually switch these around. Again, it won't work with k values less than 3. And otherwise, I want to use the forward differentiation. So if I run this, I see I get slightly different results here. Let me put side by side here. Actually, I'm going to put these all on top of each other so we can compare them right away. And I'll get rid of that title, and I'll put in a legend. So forward and backward so far are the two we've used. So if I plot this, we see with the two techniques we do get two different estimates as to what the acceleration is based on the same velocity data and the same time data. So they do agree pretty well once we get to 5 seconds. The forward and the backward are pretty much the same, but before that they are a little bit different in their techniques. Although even with the forward differentiation, remember it ends with a backward differentiation, and the backward differentiation actually begins with a forward differentiation. So that's actually why at 9, 10, 11 they agree exactly, because they're both backward there. At 0, 1, 2 they agree exactly because they're both forward there. So it's really in the middle here that they're actually using one technique versus the other. Alright, so let me now look at using, get rid of this, central differentiation everywhere I can. Again, using accuracy of 2. Looking on the table, in order to use an accuracy of 2 central differentiation, I have to use the point before, and I have to use the point after the point I want to know the derivative of. So actually, I have to start with forward differentiation, since I can't use the first point with central. So if k is 1, is really, well, I'll just make it, if k is less than 2, I have to use forward differentiation. Else if, then I have to use backward differentiation once I get to the last point. So when k is greater than 11, I can no longer use central differentiation. So this is new. Otherwise, I can use central. And here. If I look at the table, to use an accuracy 2 central differentiation, I'm going to take negative 1 over 2 times v of k minus 1, and I'll add to that 1 over 2 times v of k plus 1. And then I divide that by my time step dt. And I'll plot this in green, and we can see what this looks like. So again, we get another different estimate here. The central differentiation begins with a forward, so all 3 agree at 0. The central ends with a backwards at 11, so all 3 of them agree at 11. But the central is different than the rest in the remainder of what we have going on here. Right, so 3 different techniques, mostly using forward, mostly using backward, mostly using central. I'd say for data we've already collected, probably central wherever you can is your best bet to have the best accuracy. But if this was real-time data, then backward would be the only way we would want to go. Forward has its uses, again, especially at the beginning where we don't have any data previous to it, then we have to use forward to start. But then we can switch over to central, and then we can switch over to backward differentiation. Right, so again, with the 3 methods I took, remember I can't use one method for every point I have, because eventually I'm going to run out of data before the point or after the point, so I might have to mix what I have. But make sure that if I'm mixing, that they all are using the same accuracy technique. And be careful here, because if you're trying to take a point that doesn't exist, like the 0th value of v in this case, or the 13th value of v, then it's not going to like that because that does not exist. So you have to be careful where you're putting these if statements if you're using this compound approach here of using sometimes forward, sometimes backward, and sometimes central differentiation.